So always good to give you guys a few reminders and update you on things that are coming down the pike ahead of these seasonal changes. So we'll do a quick recap of decision support services and the changes to our briefings coming up this season. We'll also look at a hazard simplification change that's going to take place in mid-November, middle of this month. And then non-weather emergency messages is something most of you probably at least heard about in a tertiary sense at least, but we'll dig a little bit deeper into that. And then Larry will finish us off with just a winter resources refresh. So as I mentioned before, not a whole lot of substantial changes. Last season, we made the choice to go to more of an event-driven format, which is what we're sticking with for this one as well. Of course, most of you probably know we're getting ready to enter a period of strong wind gusts. See the wind picking up now. We've got high wind warnings out in some places and wind advisories elsewhere. So never a dull moment. There's always something going on. And you've probably seen some briefings go out to that effect here in the last day or so. The idea is that the briefings, the frequency will increase as we get closer to an event, and as we become more confident of something more high impact, then we begin triggering the more live briefings, the in-person briefings that give you an opportunity to ask us questions. And we also have the weekly outlook. This is something that I think we started last fire season, but it really took off, and so we continued it kind of through the fall. We're really going to a year-round format with these now, so we'll be sending these every Sunday, although the focus will shift more to our fire weather partners once we get into the peak of fire season. The exception to that would be if, say, we have a thunderstorm event coming, or one of those rogue rain events or wind events, which typically don't happen in the summer too much, but every now and then they do, and in that case, it would loop in everybody. So for our email briefings, you probably already noticed there's a bit of a change to the format. A couple years ago, we went to kind of this one-pager format. We used to just send kind of a block text format with a bunch of images, and we moved to something a bit more consistent and organized a couple of years ago. That's changed a little bit. The general flow of the briefing hasn't changed a whole lot, but they did make some changes to the colors. And a lot of that had to do, the colors that indicate the impact, a lot of that had to do with some color blindness studies that were done. And they wanted to make sure the color scale would conform to those who have colorblind sensitivities. So they did make that change. And then we've moved to more of a tabular format for our details instead of just kind of bulleted text. And that includes that confidence column that Ed pointed out. So the example here, which is just kind of rotating back and forth through the two-pager, shows that confidence column. And usually we'll just kind of emphasize in the details section the specific weather hazard we're forecasting, and then give a rundown of what kind of timing we're looking at, what specific impacts are going to fall out of that, and then our confidence in that happening. That's kind of how we're laying that out. Just to take it a little step further on the color scale, to give you an idea of what these colors mean, when you go back on the one pager and look at the weather and impacts outlook there, it's kind of the broad 10,000 foot view of impacts for the next 7 days. This is really what's supposed to inform those colors. So it's not just based on the impact alone. It's also supposed to give you an indication of how confident we are that that impact is going to take place. So if we're looking at something that's going to have a moderate impact, but we're not terribly confident about it, 33% or less probability of happening, then you're going to probably see more of a yellow shading. If we're looking at something that's 2-3 days away and we're already shading it orange, that should tell you that we're more confident something more impactful is going to happen. It's kind of how that works. Our live briefings are changing a bit this year too. Last year we moved to a PowerPoint template. And this year there's actually IDSS, Decision Support Consistency Team, within the Western region of the Weather Service. And they developed a Google Slides application for us to use. And so we'll be moving over to that Google Slides application. The briefing you're seeing on the left-hand side there, that was basically just a base blank template. So you see a lot of blank space there. That would typically be filled with text that would just kind of give some short snippets about the impacts, the timing, that kind of stuff. But for those who have sat in on our fire briefings, we moved to this tool for this last season, so they're going to look very similar to that. But really, it's a really great tool. We're able to quickly update our graphics, update the text and the key points and things like that. So we're really excited to unveil this and use it this winter season. We will host those webinars when we do have them at 10:30 in the morning, as they've always been done in the past. And it's just one of those situations where we give you more of an opportunity to meet with us in person and then express any concerns you might have or ask questions about the upcoming event. I mentioned we are going to continue with our weekly outlook. We did have one go out. I think we started these 2 or 3 weeks ago. So they will go out every Sunday, usually sometime in the afternoon. Occasionally, it could be in the evening if we're still waiting on, details for a particularly impactful event. But it's really supposed to be kind of that week-long overview, what's coming in the next week. And that's just kind of that regular briefing presence that goes out. And that's just a PDF. We don't conduct those live. But that'll just go out as a PDF with slides. All right, moving on to hazard simplification. HazSimp has been going on for a number of years now. They've looked at trying to whittle down the total number of watch, warning, and advisory products that are out there because we just have an insane amount. And as part of that consolidation, we're moving on to hydrology now. And so our local implementation date for this is November 16th. Us in Spokane will be doing it at basically the same time. They're our backup office, so we want to make sure we're in lockstep with them in case something happens. So essentially what hydro hazard simplification is all about is taking all the different flood watch and flood advisory types and really just condensing them into one of two things. So the flash flood watch and traditional flood watch in most cases is going to go just to flood watch. And then all these flood advisories over here, like urban and small stream, hydrologic advisory, those are all going to go to just flood advisory. So we're eliminating a whole bunch of products and kind of putting them all into one basket, more or less. The one caveat I will note with flood watches is we can still issue flash flood watches for instances where we're concerned about burn scar flooding, because it's a very targeted, very precise, location and precise type of event, or a dam break potential. So that's the only cases where you're going to still see a flash flood watch potentially, but otherwise, like 98+% of the time, it'll be a flood watch. Also going to be moving to more of an impact-based format for the actual text. So for the flood watch, the flood watches and all the advisories, we're going to move more to that what, where, when, and impacts type format, which is a lot easier to read. It's much more digestible. Flood warnings and watches as they exist now are quite lengthy. I mean, they get very, very long. So we're going to be moving more to that format. It should be a lot easier to read and understand. So that's hazard simplification. That's kind of the only major thing with that's taking place right now. It's a multi-year process, so they're kind of tackling different aspects. I don't know when the winter ones are coming, but I don't think it's going to be this winter. I think that's maybe next year. So we'll keep you up to date on those, though. All right. And then lastly, before we get to Larry, I'm going to talk briefly about non-weather emergency messages. All the different possible non-weather emergency messages are listed on the left-hand side there. The ones that folks are probably most familiar with are the child abduction emergency, the Amber Alert, the civil emergency message, CEM, or perhaps the avalanche warning. Aside from that, there's a lot of these that we don't typically issue all that often. But with non-weather emergency messages, the whole idea is to bring greater consistency to the process of local alerting authorities, like the county emergency managers, public safety folks, giving them a uniform, consistent conduit to pass that information on to NOAA weather radio. So that's kind of the basis of it. Because in the past, it's been very ad hoc, where one county might have this agreement set up with our office and another county has a slightly different agreement set up with our office. And so it just gets very confusing. The way the flow of alerts goes is it goes through what they call a collaborative operating group. And it has to be authorized by FEMA. So for those who are interested in possibly sending out these non-weather emergency messages, you have to go through a process to get authorization to send them. And it can go through IPAWS. So once that occurs, essentially, you'll have authority to send these alerts through IPAWS, which is, I think, the Integrated Public Alert and Warning System, to the National Weather Service. It can also go to EAS. But essentially, the flow is from the left here, from the alerting authorities through what they call CAP software. A lot of times, I know a couple of the different software vendors are like AlertViz, Code Red, it's Everbridge, I think maybe one. Anyway, there are a number of different applications that can enable this feature, and if you essentially select no weather radio, it'll pass that through to us so that we're able to actually transmit that via weather radio. And it just gives you another conduit to get information out, essentially. But it doesn't include the emergency alert system stuff or wireless emergency alerts. We don't really have any control over that. So that's kind of how that process works. For our internal, office, how it affects us is, once you are set up to send out alerts like this, and you toggle the National Weather Service on that you want it to go to weather radio, we'll get this banner in the office. We'll actually take a look at the message. Sometimes there's some wordsmithing that's got to go on because our computerized voices don't always pronounce things all that well on weather radio. And then we'll push it over to our weather radio. So that's kind of essentially how that works. There will be times where you might have to modify the wording a little bit, and partly for readability, but we may also have to clarify certain things, because sometimes you're putting these things together pretty fast. So we may need to get some additional details or clarify certain segments of the message. So not at all unusual for us to coordinate with whoever it is that's sending it to make sure we know exactly what is needed and what needs to go in that message before we actually transmit it. And again, I'll remind you, all the slides that we're presenting today will be made available, so you'll be able to reference this after the fact as well. The general timeline for rollout, I drew all this for a presentation that was given for the state of Washington. So the offices listed here are essentially all the offices that cover Washington. Seattle has already more or less trained all their staff. They're capable of sending these now. We're targeting a date of December 1st to be able to, get everyone trained up so they can receive the messages, go in and modify them, and then send them out. So we're doing some step-by-step training with folks in the office, and hope to have that by December 1st. Of course, with the holidays coming up and various other things, it's possible it could get pushed back, but we're trying to adhere to this December 1st deadline. And now, Larry, I'll pass it off to you.
Okay, great, Mark. Are you advancing the slides, or am I?
I'll advance. You just tell me when.
Okay. All right. I was going to talk today about probabilistic snow. For those of you who were part of this presentation last year, I did a rather lengthy presentation on probabilistic snow. So this year, I'm just doing a bit of a review in the interest of time. But if anybody certainly has any questions or wants more details, I could take those questions or provide that information either via email or chat or whatever once we get done with the IWT. To go very detailed in this would take quite a bit of time. Alex and Ed have already shown some of these slides and talked a little bit about probabilistic as well. So some of this may overlap some of the things that they've said. But we now have on our probabilistic page, and I'm going to show that towards the end. But basically what we're doing here is rather than just putting out one number for snow, we're going to be talking a little bit more, and we'll be providing these as part of briefings as well, what our expected snowfall is, what a low end amount is, and what a high end amount is. And then there's some additional briefing, and there's some additional tabs that you can see there at the top as well. But next slide, please, Mark. Generally what we'll have, and there's going to be on the left a larger image, which is the expected snowfall, which is the official National Weather Service forecast and the most likely scenario. This forecast is actually prepared by a forecaster or forecasters, at the National Weather Service office here in Pendleton. Generally, this is considered to be about a 70% likelihood of happening. All human, made by human forecasters, based on the guidance that we see, based on our experience in the office. Then there'll be on the right-hand side of the page, there'll be two images, one at the top and one at the bottom, a high-end amount and a low-end amount. The high-end amount is generally considered to be about a 10% chance, a 1 in 10% chance of it happening. And that's generally considered to be a reasonable worst-case scenario. And then the low-end amount is about a 90% chance of it getting at least that much. Now, of course, if you have a 90% chance of, let me start again. I messed up my words there. If you have a reasonable worst case scenario, a 10% chance of that happening, there's still a chance that you can exceed that amount even. These two are run on a cron job. Now that we're in standard time, it will run about 4:30 a.m. and p.m. The cron takes about 15 minutes to run, and then the images will post usually about 15-20 minutes later. So you'll see these on our website around 5 a.m. and 5 p.m. Now, just because a cron job runs at 5 a.m. and 5 p.m., if it's 9 o'clock in the morning, let's say, and we're looking at data, the day shift comes in and is looking at data and says, wow, it looks like we're going to get significantly more snow now, or we're going to get significantly less snow now, we can manually run the cron job anytime we want. So if we're looking at data and we think it's going to be a lot more snow or a lot less snow, we're not going to keep that forecast on there. That could be 7-8 hours old. We can change that as well. So now in the cron job, there's forecasts from WPC like Alex talked about earlier. There's different computer models. There's ensembles to the computer models. There's probably about 40 or 50 different forecasts that go in that. So hopefully when you see these ranges, they're not going to be hugely different, but sometimes they can be. Next slide, please, Mark. If you see a lot of variability between the high end and the low end forecast, what that generally means is that there's a lot of variability in the models. But what we also have on the website, you'll see images towards the bottom will be individual probabilities for 1/10 of an inch of snow, 1 inch of snow, 2 inches of snow, 4 inches of snow, 8 inches, 12, and 18 inches. We only captured 3 of them here for 1 inch, 4 inches, and 8 inches. So in this case, say for Pendleton, it's a 12% probability, 0% for 4 inches, and 8 inches is 0%. So various different areas, but if you were specifically wanting to know, is it a high, chance that we're going to see 1 inch of snow? 12% isn't all that high, and it's a 0% chance that we're going to get, anything higher. If you were looking for the Cascades, for somewhere like, some of them high mountain passes, there's a very high probability, approaching 100%, that we're going to get 8 inches of snow in this case. But you could also, if you're trying to extrapolate out, if a location has a 90% chance of seeing 2 inches of snow, but only a 30% chance of seeing 4 inches of snow, a reasonable estimate would be between 2 and 4 inches of snow. So that's one way that you can look at some of this information. Next slide, please, Mark. But beneath these images is a snowfall table. Some people like to look at the pictures. They say a picture's worth 1,000 words. Some people like to look at the individual cities or towns. but it basically just takes the amounts. Most places, most counties in our area have at least one town mentioned. Umatilla County has 5 or 6. Some other places may only have 1. But you can take, and it'll give you the range there. For example, again, Pendleton, 72% for a trace, 34 for 1 inch, and then basically zeros for below that. If we took Trout Lake, it's basically 100% until we get to 8 inches, and then it starts to drop off. But it's a great way just to take a quick glance for specific locations, and it summarizes the values as well as the low end and the high end amounts there that you could expect. And you can see where there is a greater variation for single locations, and it indicates lesser confidence in the forecast. So for somewhere like, I don't know if we're going to have a good example. Well, even for somewhere like Trout Lake, it's 100% until you get to 8 inches, it's 96% or greater. But by the time you get to 18 inches, it's barely a coin flip. It's barely 52%. For Meacham, it's 100% until you get to 12 inches. And then it really drops off for greater than 18 inches. It's about a third, 33, 34%. So you can see where the big drop-offs occur. So this actually isn't a bad example, and this is actually using live data. So sometimes taking a look at the table can be just as good as looking at the charts. Next slide, please, Mark. How to gauge forecast confidence. Again, the differences between 6 to 8 inches between low or high end amounts can show differences in in forecast confidence, but it's also you may see sometimes very high amounts, especially in the high end amounts over the higher elevations. But that also shows you where there's differences in forecast confidence, and the same thing will apply even at the lower elevations. If the low end amount is 1 inch and the high end amount is 10 inches, that basically shows that there's quite a bit of different forecast confidence issues. As the range increases there, confidence will decrease. If there's a small variation, then we have much more confidence. Next slide, please, Mark. So how are we going to use this? Probabilistic products are ideal because they can provide a wide range of possible outcomes as opposed to a single forecast. It helps us answer the "how confident are you" question. It can help decision makers who require threshold values for certain actions to determine the probabilities of those values being reached. Maybe you need to take a certain action if you're going to get 4 inches of snow. Well, you can take a look at that 4-inch of snow map and see what the probability is. Maybe a superintendent of school needs to decide whether they're going to close school tomorrow if a certain accumulation is met, and they can see what the probability is of that value being reached. Or maybe a Department of Transportation has certain actions they have to take if certain ranges are met. Every event will provide scientifically based reasonable worst case scenario, which can be used by various emergency management and transportation agencies. And remember that the high end amount is a reasonable worst case scenario, and there's still about a 10% chance that reasonable worst case scenario can be exceeded. I saw some data that's a couple years old now, but there's about an 80 to 90% correlation that the snowfall usually fell between the low end and high end amount about 80 to 90% of the time. And additional resources are available if you clicked on the tabs at the top of the website. Those are ice accumulation, the winter storm severity index, which Alex touched on earlier, long-range forecast information. And again, the link to get to these, our website is weather.gov PDT. And if you just do another / and winter, you can go to that. And if I did this right, Mark, that's actually a link. If you click on that at the bottom there, that will actually take you to the live to the website.
When I share the PDF, it should be clickable. Should be a clickable.
Okay.
Yeah.
Right. So that's actually a link to the website where all of that information will be available, and you can click on it. The ice accumulation, just one point of thing to mention with that, with the snow you get 3 maps, with the ice you only get 1. You don't get a low end amount and a high end amount of ice. Ice obviously in this area is a lot less frequently occurring, and that's a good thing. So you'll just get a most likely ice accumulation map. You don't get a low end and a high end. Usually the ranges for ice, a couple hundreds to a tenth or 2. So there's really no, there's not enough scientific knowledge to make a high end amount that may, if the likely amount is 400 or a tenth, the high end and low end are going to be so close to that there's just not enough science behind it to make it, there you go, to make it stand out differently, that it's going to be so close to it that they just don't split them out into low end and high end amounts. So it's just one map. And that is all that I have. I can certainly take any questions. And if anybody wants any more, like I said, if anybody wants any more details on this, you can certainly feel free to email me, and I'd be happy to take those questions later. For the interest of time, we've kept this relatively short.
Yeah, I think so. I think let's if you have a question, maybe just go ahead and jot it down. We can either get to it at the end of the presentation here or the end of the meeting, or I can follow up by email. So let's move on to our next presenter because we are running a little behind on time. We have Nick Bond, who's the Washington State climatologist, and he's going to be talking about climate change and its influence on Pacific Northwest winter weather trends. And Nick, you should be able to unmute yourself when you're ready.
Yeah, I think I am unmuted, but
you are. I can hear you.
If otherwise. So is this scene going to be playing out less and less across the Pacific Northwest? That's the question, right? All right, next slide. Yeah, I'm just give you a whirlwind tour of some of the things that have been seen out of the Washington Climate Office. And here, kind of taking a Pacific Northwest perspective, there's some tidbits here for the Pendleton area, but certainly some examples drawn from other parts of the Northwest. Next slide. And they are not just things like temperature and precipitation, but also more short-term events like cold snaps and windstorms and so forth. And so we're going to be reviewing both the historical data and what some of the climate models are showing. All right, next slide. All right, I'm starting off here with some published results from a paper some years ago. It didn't include some of the warm years that we've had in the last decade or so, but there for the 4 different seasons, winter, December through February, spring, summer, and fall, what the temperature trends are color-coded across the Pacific Northwest. And you can see the lot of red dots showing that a warming trend over that 90-plus year period. And in general, let's restrict ourselves to winter, a little bit more warming in the nighttime temperatures than in the minimums rather than the maxima, which would be expected given enhanced greenhouse gas concentrations and all that. All right, next slide. When I was looking at the slides this morning, I'm not sure why I picked the west slopes of the Cascades in Washington, but this is representative of any of the climate divisions in the Pacific Northwest. And in particular, this is for the winter, November through January, the wettest season. The annual totals going back to the 1895 or so, no real trend in the precipitation in winter around here. lots of year-to-year and even multi-year variability, but yeah, a lot of noise, but not much signal there, at least yet. All right, next slide. Minimum temperatures, and just a different perspective compared to the map, the dots that I had on that previous slide a couple ago. And here, just again, looking at the year-to-year variations. This is for Washington State as a whole. It'd be very similar for the climate division that Pendleton is in, with really cold winters just don't happen as often as they used to. And but there's still plenty of variability there. So, all right, next slide. This may be a little more complicated plot, but looking at snowpack, in particular, the end of winter snowpack in terms of the snow water equivalent, with those dots in the left-hand panel indicating the trends at the different locations. The middle panel, what I actually like you to focus on perhaps more, is both the observations kind of run through a hydrologic model, the VIC model, to kind of back out what the snowpack was like at the end of winter. And with those red colors showing where there are decreases, blues where there are actually increases over that period from 55 to 2014. And then on the right, an interesting thing that Mote et al. Did was looked at what the contributions of temperature and precipitation were to those trends. And what this shows is if you took out the temperature effect, that right-hand panel shows what the trends would have been in SWE on April 1st. And what that shows is in a lot of the Pacific Northwest, there was actually over that period, 55 to 2014, some increases in precipitation that kind of counteracted the warming that has occurred, such that the decrease in SWE wasn't as much as it otherwise would have been. So I hope that was clear. Just in the interest of time, let's keep going. So next slide. Of course, for much of us who have been around here, for a while, the winter of 2014-15 was still vivid in our memories. This is the scene in the Cascades of Central Oregon. Not too many people actually shredding that season. Next slide. And so that year was kind of a wake-up call in a way for the climate community, and showed just how, with a warm winter, just how bad the snowpack can be. So, but now I'm going to shift gears and a little bit into more of the event scale stuff, and using the example of Spokane. This is some just results I had for a previous presentation some time ago. Just counting up how much snowfall each winter back to the 1890s, you don't get any sort of impression that the amount of snow, at least at this location, is really changing much. Obviously a tremendous amount of year-to-year variability. All right, next slide. Another on the event scale, here Ritzville in the Columbia Basin, about halfway between Moses Lake and Spokane. I counted up just the number of, for there, what would be a cold winter day, the blue trace there, days that has a minimum temperature of 15 Fahrenheit or below, and for what it's worth, a number of kind of warm summer nights with 60 degrees and above. And there is a bit of a downward trend in the number of cold events. Next slide. Olympia Airport, kind of a cold spot in Western Washington. Maybe a little bit, if you use your imagination, of a downward trend in the number of cold days. Certainly an upward trend in the number of warm summer nights. But yeah, a very noisy signal. And even when you're looking at the data over multiple decades. All right, next slide. Here, what I think is really interesting, again, I'm the Washington State climatologist, and apologies that I didn't have the data right at hand for Pendleton and Redmond and so forth. I've got a few examples coming up, but here what I looked at was just over the period of record the coldest day each year. And what I think is interesting here is basically the absence of trends. And to me, this actually makes sense. We know that there have to be special dynamics to have a really cold day in the Pacific Northwest. You got to get the air from Northwest Canada down here and so forth. And so it is more. The trends here are that the very coldest days aren't any that much warmer, maybe a little bit, than they were in decades past. And so again, this is kind of more a dynamically driven sort of a feature, and the lack of trend here maybe isn't such a surprise. All right, next slide. Some things, though, that we are seeing are in many mountain locations, and going back to the results from the Mote et al. Paper, where the snowpack is declining. This is an example from the North Cascades, showing plenty of year-to-year variability, but a downward trend with the 2015 winter there, the all-time low being the, at the end of this particular series. Next slide. And that has implications for our streams in the Pacific Northwest. And there are, they've been divided into three categories. One, mostly, well, low elevation watersheds that are rain dominant. The ones that have a combination of lower elevations and higher elevations, so they get both some floods during the heavy rains in the winter, and then another pulse of water in spring with the snow melt. And then there are the snow dominant ones, the higher elevation ones that their biggest flows are during the spring snow melt. And what we see is on these rain dominant ones, the Chehalis River, and in my next slide, I'm going to have a couple of examples from Oregon, that maybe overall not too much of a trend in the biggest flood each year, but some hint, at least, that the very largest floods in recent decades have tended to be larger than they have in the past decades. What we really see are the trends in the higher flows are on these mixed rain snow watersheds like the Stillaguamish. They're off the west slope of the Cascades in northern Washington. Don't really see much trends. If anything, maybe a little bit of a less of springtime floods in the snow-dominant rivers. We go to the next slide. There's a couple examples from Oregon here, and on the left is a rain-dominant river, the New Halem, Tillamook County, Western Oregon, and on the right, more of one of these mixed watersheds, the Sandy, reaches on Mount Hood, and then flows westward. And so the example there that maybe in these kinds of watersheds, we are seeing some tendency, and it's slight with a lot of noise, for greater floods in recent decades than there have been in the historical past. And we expect that especially to occur on the rivers like the Sandy. All right, next slide. Let's skip this one. Who cares about summer? That's the Lampastus. A number of rainy days. That's another really, the suggestion is in some places that we're getting the heavier precipitation events, and maybe that is the case, but boy, it's pretty noisy data. And these this example from SeaTac and Spokane doesn't really kind of indicate much of a the tendency for necessarily more rainy days, but there is that potential, and maybe Seattle is kind of showing some upward trend there. All right, next slide. I encourage you to explore some of this stuff for yourself using this really slick application we have on the our website, in which you can bring up for temperatures, precipitation, snowpack. You can bring up these maps for different times of year. Look at the trends. You can adjust the starting point and the end point. The dots show where the data is and where the trends are significant and maybe one way or another, but not significant. And then if you click on a dot, it can give you a time series right at that point. So if we go to the next slide, it just shows an example here of looking at just the last 30 years. And here, winter, looking at temperatures, you can see there's both blue dots and red dots, but none of them are statistically significant. And that's basically because any sort of trend over a period as short as 30 years is really pretty marginal. And just very sensitive to what the conditions were like both at the endpoints of that the period considered. Next slide. Here, just an example for a place, well, near the office here in Hermiston, just kind of showing why you could get such ambiguous results. If you were to look at the temperature trends, let's say starting from the early 90s to the late 2010s, you'd actually get a negative trend. You get a pretty strong positive trend if you started in the mid 80s and went to the, the disaster of the 14-15 year. And so it just shows, and be really careful about a trend analysis with shorter periods. All right, a few more. One thing you're a good spot here about winds, and something I'm particularly interested in is whether, any signals emerging there. These are 3 Washington stations. Here I just count up the number of hours using that had wind gusts exceeding 39 miles an hour. And it looks like, well, maybe it's getting windier. But I'm really skeptical here about the change in technology from the cup anemometers to the sonics at the ASOS stations and reporting practices and so forth. I don't know if this is real or not. Go to the next slide. And so I did some other things thinking, well, maybe the mean winds are better. And this is a mess, I know, but I wanted to get an Oregon place in there. Astoria in the blue is the number of hours with strong mean winds. There doesn't seem to be any trend there. Not really much of a trend in the hours of strong gusts either. That's in green. And then the red, again, just arbitrary picking when there was low sea level pressure and presumably, more storminess. And yeah, so this is still an open question. And the very next slide, I think, will, just reinforce that idea. And here, okay, I looked at 3 places in Oregon itself. And this is Redmond in orange. Blue is Pendleton, green, Astoria, the number of hours, again, with this 39 miles an hour just picked arbitrarily. And you might see, the suggestion is, well, maybe it's going up, but something's amiss here. I am not prepared to believe that there was not a single gust exceeding 39 miles an hour in Redmond over that 20-year period or whatever. And I think, again, there's just something having to do with either the technology, the reporting practices, or both. And so while the suggestion is maybe it's, the frequency of high gusts is going up, it remains to be seen. All right, I just want to take a couple of minutes now go to the next slide, on what the models are showing. Next one. Right. Temperatures has stopped the presses. Hey, it's supposed to get warmer, right? Looking in the upper left for winter time. The ensemble average of the with the RCP 8.5 scenario for the temperature change from basically in the middle of this century compared to the end of the 20th century, with greater warming inland where there's less moderation by the ocean, which has a lot of thermal inertia. All right, next slide. In terms of precipitation, wetter in the Pacific Northwest in winter, drier in summer, but note that the scale is different here. And so much wetter in winter and just somewhat drier in summer that's already quite dry. So more overall water is what the models as a whole are showing. Okay, next slide. And there, the real separation in what the climate will do in terms of the temperature is basically going to be seen at the end of this century, or in the second half of this century. With the 4.5 scenario versus the 8.5 scenario, these are individual model runs. They basically overlap one another until about 2050 or so, and then tend to diverge. And so whatever, the climate powwow in Scotland right now, whatever is both decided and acted upon there, won't really make a difference until later this century. A lot of warming in the system is already baked in. All right, just a couple more, I promise, and then we can. And there, I want to kind of point out another tool that I think is pretty slick, and that is something about time of emergence. And the Climate Impacts Group at the University of Washington has put together some materials there that are kind of based on the climate model projections, looked at various sort of impactful weather events. And here you can see from the model average, the orange diamonds or squares, whatever, that for different duration events for a grid cell pretty near Pendleton, what the expected change is in the 2050s in terms of the magnitude of that 25-year event on different time scales versus in the historical past. And so, yeah, the expectation is that heavier precip events are going to be heavier, but not a huge amount more, maybe 20%. Another perspective on that is on the next slide, where you can look here, just picking a 24-hour event, how that is liable to, the change is going to play out over the rest of this century. And again, just very slow increases in the magnitude of that event, projected, of course, versus in the historical past. And then I think I have one more slide showing one of the goodies here. There's other sorts of products here on the kind of time of emergence, in which you're looking at basically when the signal gets to be something like 2 standard deviations above the noise in the climate. And here's an example. Just when will the warming in January kind of exceed that year-to-year variability? And it's done on a county-wide basis. And so you can see for yourself in various parts of the Northwest, maybe that climate signal has already emerged from the noise. In other places, we're going to have to wait a little bit. And this is, again, based on the climate projections. Okay, I think I just have a summary. The atmosphere can always play tricks on us. So, this is all with the attendant uncertainties and so forth. But next slide, I think I've got some words just to, forget the first point, the heat wave, past history, right, ancient history. We are getting minimum temperatures in the winter that aren't as low as they used to be. We're not seeing it yet, but we're expecting winter precipitation to be on the increase. And at least in some watersheds, the there's implications for more flooding, and of course, what you do to with the reservoir operations to save the water for the dry summers. And then I wish I could had something more than just some very ambiguous results about windstorms, but don't have that. And with that, I appreciate your attention and your apologies for kind of blasting through this stuff. But in particular, I know Mark is going to make the PDF available. And if you have any questions, please get back to me. Thanks.
Thanks so much, Nick. Always appreciate the humor infused in your presentation. So it's always good to break up the monotony a little bit.
Yeah.
All right. We are running just a little behind schedule, but our last presentation here is Gabe Collar from the Central Oregon Avalanche Center, and he's going to talk about avalanche forecasting in Oregon. So, Gabe, you should be able to unmute yourself and take it away.
Awesome. Hopefully everyone can hear me.
I can hear you loud and clear.
Sweet. Yeah, I didn't know the general audience. This is my first one of these meetings for me, so I kind of kept it kind of brief and simple, and just kind of wanted to explain our day-to-day operations and what that looks like as a product we deliver to our user group, and then how that fits into the warning system, the Avalanche warning system. If people have more advanced questions and stuff like that, we can definitely delve a little deeper, although short on time for sure. Just some pictures here of some of the avalanches I've taken pictures of for the forecast center since I've been working as a forecaster. And they range in size from the upper left one, kind of smaller avalanche, something we see pretty regularly in our backcountry ski terrain and our mountains. The picture in the upper right, pretty massive avalanche. The slab of snow that fractured was over 6 feet deep, so definitely enough to bury a house or small structure. And then on the bottom, that's the west side of Mount Jefferson, and huge amount of avalanche debris there from a rain on snow event. The one thing all these pictures kind of just coincidentally have in common is they're all in the backcountry. They're all places where people go to recreate, to climb mountains and ski. But in Oregon, at least, not 100%, but a lot of our avalanche terrain does not impact, the town of Bend or Highway 97. A lot of our infrastructure is outside of that avalanche terrain. We don't have a lot of high mountain passes and stuff like that. There are definitely some exceptions. We'll talk a little bit more as I get into it about how that impacts our operations, and also how that plays into the warning system and stuff like that. Kind of just the nature of our terrain, right? The peaks bump up high, and there's not a lot of towns in the mountains. Go to the next slide, Mark. These are our 3 avalanche centers that we have here in Oregon. This is a picture of the National Avalanche Center map that covers all of the United States. Just zoomed in on Oregon. And each of these centers is kind of disparate almost. It's independent from the other ones. On Mount Hood, we have the Northwest Weather and Avalanche Center, which continues all the way up through Washington. One of the bigger avalanche centers in the country. And then we have these 2 smaller independent avalanche centers, the Wallowa Avalanche Center and the Central Oregon Avalanche Center, which is where I'm based. Obviously, a lot of what I say might be specific to the Central Oregon Avalanche Center. I'll try to be clear when that's the case or when it's not. And just some of the differences in these centers, the bigger center, like they have on Mount Hood, they're issuing a forecast for 7 days a week, whereas Wallowa's, I talked to Victor and he said they forecast Thursday through Sunday, just covering the weekend. And similarly, we issue forecasts on Friday through Monday. Cool, Mark, you can go to the next slide. And this is just, this is what we do. Like I said, we don't have a lot of infrastructure in avalanche terrain. As avalanche practitioners, when we talk about avalanche terrain, we're generally talking about a snow-covered slope that exceeds 30 degrees in steepness. That's what we need to produce avalanches. And since we don't have infrastructures, you know, it's not dissimilar to maybe Utah or Colorado or something where their forecaster might go out and drive the highway and see what avalanched over the course of the preceding night. We have to actually go out into the mountains to see what's going on. So we rely really heavily on a lot of field work. And that's usually a forecaster or a professional observer out on skis, covering through terrain, looking for avalanches, and also digging in the snow, looking for that weak snow. We're always looking for weak snow that can cause an avalanche, basically. We're always looking for weak snow. We do that through targeted snowpack tests and also just observing, you know, what type of snow is down here? What do the grains look like? We also are making detailed snowpack observations, whether that's just like the pure height of snow and how that varies over terrain, as well as the weather. You can go to the next slide, Mark. And then we're taking that information. We have, I guess just to continue on the last slide, you don't need to switch. We have 2 forecasters here at Central Oregon and 2 professional observers. So we definitely have someone in the field 4 days a week. And all of those individuals also work as ski guides where they're out in the backcountry, kind of with the same mindset, trying to avoid avalanches and trying to make their best guess as to where the avalanches could occur. So that's where all of our field information is coming from, is those observers and forecasters, whether they're on a paid day for the Avalanche Center or working for a different job, kind of double duty in it. We're going to bring that information back into our office or our home and spend a lot of time just looking current data throughout the region, whether it's webcams, like I've included a screenshot of the Mount Bachelor snow stake there, or the middle shot is our weather station that we operate up on Moon Mountain at 7,000 feet. That's another problem. We have a lot of our weather stations, as opposed to other areas where there's more in the mountains. We don't have that many weather stations up high. You know, we're trying to write a forecast for 9,000 feet, and the best we've got is a couple weather stations at 7,000 feet. Or looking at satellite. I just included a few images here. Obviously not going to paste them all on there, but we're looking at satellite imagery. And then combining that with the weather forecast that you guys make, just things that are particularly useful to me is the forecast discussion. That's usually where I start, just to get a big picture idea of what's going on. Probability of snow. That's a pretty awesome trend. I've really appreciated hearing discussion in this meeting. It's awesome. I'm psyched. Really, really useful to us. A lot of our avalanche types here in Oregon differ from maybe in Colorado or places in the Rockies where they're more worried about the snow that's already on the ground, avalanches that are going to occur in that old snow. We're more worried about avalanches that are going to occur in new snow that's coming in with storms. So, you know, forecast for snow is huge. That's what I spend most of my time hemming and hawing over. And then lastly is another product that Mark generated for us, just a little more specific 3-hour forecast and mountain specific. Has snow levels are really helpful for us, and precipitation probability again. That's just some of many of the things we like to look at. Go to the next slide, Mark. And then we're going to take that, and this is the forecast that we generate, or an example of it. I don't know if folks have ever looked at this before or if it's all new information. You can dive deeper into it or kind of stay on the surface. I think the key is, or the part that's probably most useful to the general public, is that avalanche danger, where you see that triangle with the yellow top. That's meant to represent kind of your theoretical mountain, with the top of that pyramid or triangle being your alpine terrain. That's maybe like, you know, the top of Mount Hood, to use a common example, I guess. And then the middle elevation band would be near tree line. Maybe that's Timberline Lodge or some of the ski areas. And then the bottom band is below tree line. So that's maybe, you know, government camp. And that's really how we break up the terrain. We break it up by elevation that way. We also break it up by aspect a lot. And and we're going to assign danger, our avalanche danger, based upon that elevation. As you read through it into the image on the right, gets more specific into like the types of avalanches that we're predicting and where they're going to occur, what size, and what their likelihood is. And then as you just keep reading, it just gets more and a little more specific. But I think there's a lot of research now that a huge percentage of the public is really just keying in on that avalanche danger, and they're not really going a lot farther. You can go to the next slide, Mark. And this is a schematic or the matrix of avalanche danger, how we're assigning avalanche danger. Keying in on some of the other talks, I think it was Ed was talking about really trying to pin in numerical values to these likelihoods. And that's something that's just kind of coming in the pipeline in avalanche industries. If you look at the column for likelihood of avalanches, there's all these real ambiguous terms like very likely or unlikely, possible. I think we're trying to get more into the realm of having some numerical values, but it's not there yet. This is really what this is our go-to tool for avalanche forecasting. It's really trying to fit our current conditions into one of these boxes. You can go ahead, Mark. And then the last slide I threw here, kind of went through this quick, but I know people are probably trying to get out of here. The last slide I put was the Avalanche Warnings and just the criteria we're given from the National Avalanche Center. All of the Avalanche Centers in Oregon, even though some of them are independent, we all use software and a template that's provided to us from the National Avalanche Center. And a lot of our forecasting fits into guidance from the National Avalanche Center. That's not the case for every avalanche center in the country, but in Oregon, that is the rule. So this is the criteria we would use for issuing an avalanche warning. So they're always issued when the danger rises to extreme, and they can be issued when the danger is high over a large area. Our forecast center is pretty young, and as a paid forecaster, we've never hit either of those criteria here in Central Oregon. And then the last, just for some context, the last point, avalanche warnings can be issued when non-recreationalists or people who would not otherwise access the avalanche advisory are expected to be impacted. That kind of keys back into we don't have a lot of infrastructure in avalanche terrain. The one exception we have here in Central Oregon is Highway 20, which runs over Santiam Pass. And just west of Santiam Pass, I know avalanches probably on a 3 to 5 year cycle where it might bury the road. I don't know if there's anyone from the DOT in this meeting who might know better, but anecdotally 3 to 5 years. The avalanche warning platform is used by Mount Hood. They have it on board, and I know I talked to Victor, it's used in the Wallowas. Here in Central Oregon, we haven't adopted it. And a big part of that for us has been that with only 4 days, we're only forecasting for 4 days, we don't have the staffing to maintain that warning on the days that we're not forecasting. So, if we issue the warning and we're maintaining it, yeah, warning continues. But then if no one's working on Wednesday, we can't just let that thing float or expire when it shouldn't. So that's the reason we haven't adopted it here in Central Oregon. I think as we become a bigger center, we're more likely to pick it up. So that was quick. Sorry, I was talking fast. That's what I've got.
Awesome. Thank you, Gabe, for that introduction to avalanche forecasting in Oregon. It's something I think a lot of people don't think about too much, but certainly on your mind all the time. And I do find it interesting that, with you and even Wallowa Avalanche Center, it's really just a handful of people that kind of make this stuff work. And you're getting up there and taking these observations and surveys and trying to figure out exactly who might be impacted. We have lots of backcountry recreational folks to account for. So even if people don't live above the tree line, that doesn't necessarily mean that people aren't going to be impacted.
Yeah, our user group, you know, recreational backcountry skiing and snow machining and all the winter sports are just through the roof in popularity. So every year it's more and more people out there for sure.
Yeah, everywhere, and especially in Central Oregon, which keeps expanding in population, it seems, every year. So